All right, so so most of these are U sub, but not everyone. So we'll have to kind of figure out. We'll look at it and see why this is U sub, and then I'm going to show maybe two different ways to do it. One maybe a little quicker, but the other one um, maybe a little easier in a way. So okay, so definitely if you're dealing with some kind of exponential function somewhere, I know it's multiplied by x, but if an exponential function is a part of the integrand, almost always, if it's a U sub problem, U is going to be the exponent. And then just notice if U was the exponent, so take the derivative, negative 2x, and it's just negative 2 times x. So okay, so that tells us we're going to do U sub. The fact that the derivative of our U, if we make U the exponent, the fact that the derivative is basically what's multiplied, differing by a constant, that tells us we're on the right track. So, okay, so we'll make U the exponent. Okay, immediately, 100% of the time, take derivative of both sides. Okay, and then from this, you can do it two ways. Just kind of notice you have an x dx that we want to substitute, and then here you here you have a negative 2 x dx. So we have to get rid of this negative 2 to get x dx by itself, like it is in the problem. And so just multiply both sides by negative half. Okay. Okay, now just see super clear the substitution. So first off, so you have negative x squared is U. So then this up here becomes U. Okay, and then the dx and x is here, and that's going to become 1/2 du. So we've got like everything accounted for. So now we'll rewrite this. Oops. Okay, we'll figure out the limits in a second. Okay, so notice this becomes U, so that's just an e to the U. Okay, and then the x dx is multiplied, and so now the fact that it was multiplied by x dx, now we're just going to multiply by negative 1/2 du. We'll kind of write it like that. Okay, so this is what we want. We want to go from x's and a dx to u's and a du. No x's anymore, just u and du. That's really our goal every time. If you're going to do U sub, is to have no x's and just u's and du's. Okay, so now since this has limits, this is called a definite integral. Since it has limits, we'll have to change the limits from the fact that this says dx and then these are x's means that these limits are x values. But the fact that here now it's du and u, so this tells us these have to be u values. So we'll have to find u of the top limit and u of the bottom limit, just plugging them in. Okay, and all we're doing is plugging in 1 and 0 into whatever u equals. Okay, so plug in 1, you get negative 1. Plug in 0, you get 0. So those are our new limits. Okay, and then if you're not interpreting the integral as area, it doesn't matter if the top limit's smaller. That's perfectly fine. Okay, so I'm gonna pull out the negative 1/2. Okay, and then now we'll take the antiderivative. So the antiderivative of e to the u is e to the u. Okay, when you have a definite integral that has limits, then we'll do the evaluation bar. Okay, and all that means is plug in the top limit to u, plug in the bottom limit, and subtract. All right, and then e to the 0 is 1, so it just becomes that. Okay. Oh, I hate when there's no room. So annoying. All right. Let me do this. Okay, so really u is our answer, right? So this is our answer here. Okay, I'm gonna do this just to make room. Oops. Wipe this out. Okay, so let's say we did this a different way, just in case this other ways makes more sense to people. Okay, so we'll do everything the same, you know. We're going to make u the exponent, immediately take derivative of both sides, so that part's the same. But one thing you can always do is solve this little expression that you get from taking the derivative. You can always just solve it for dx every time. So you could, oops. Sorry. Okay, so we could take this and then solve it for dx. So really just divide by negative 2x. So you'll get like du over negative 2x equals dx. Okay, and then now when you substitute, you can just rewrite everything. So write x and then e, you know, you still substitute this exponent for u. And then now this dx, just rewrite what dx equals, which is du over negative 2. Negative 2x. All right, and then notice in the next step, you can cancel out these x's. And if you do that, then you have this negative 2 in the bottom, so that's like a negative 1/2. And you end up with the exact same thing. Okay, so notice here, at this step, these would be the exact same, you know, just find the limits. So there's just that little slight different way of substituting with the dx and the du is, you know, whatever you think u is, take derivative, that part's the same, but just always solve it for dx. And then whatever dx equals here, replace your dx with that thing. All right, so maybe that's easier for some people. Sometimes, I mean, I know it's easier for some people because past years people like that way. So just another option. All right, so with practice, you could do this without u-sub, I think, but we'll do u-sub. Anytime there's like a chain rule, you know, some function within another function, you can do u-sub. So, all right, so whenever you have a trig function, a lot of times you're going to make the inside part of the trig function, the argument, make that u. Okay, then immediately take derivative of both sides. Okay, and then here we have a 3dx, but in the problem we only have a dx, so we have to get rid of that 3. So times both sides by 1/3. All right, and then now we can substitute. Okay, so notice we'll get this, and then it'll be sine. So this 3x here is u, so this will be sine u. Okay, and then this dx becomes 1/3 u, or 1/3 du. So I'll pull out the 1/3 and then just write du. Okay, so now just change the limits. Okay, and always plugging in the limits into whatever u equals. So this will be 9 and 0. And those will be our new limits. Alright, so now you take the antiderivative sign, so the thing that if you take the derivative will get you sine. So notice if it, let's say you did cosine, but notice derivative cosine is negative sign, but we want just a positive sign. So we'll make that a negative to cancel out the negative that we're going to get when we take derivative cosine. Okay, do our evaluation bar. Alright, and then I'll pull out the negative and group that with the 1/3. Alright, and then just plug in the top and bottom limits. Plug in Alright, that's weird. I don't know what happened with these answer choices. So here, let's finish this. Something's weird with these answer choices. Okay, so plug in. Oh, sorry. When I just realized the way just my view is a little different. I'm using like this video software, and I noticed this is a pi/3. It looked like just a 3. Sorry. So okay. So here we have to plug in pi/3 into this. So this 9 should be a pi. Let me fix that. Okay. All right. So okay, that makes more sense. It still seems kind of weird. Oh no. Okay, that makes more sense. Okay, so now plug in top and bottom limits into cosine. So this will be cosine pi, cosine 0, and subtract. Cosine pi is -1, cosine 0 is 1. And that's 2/3. Okay, next one they say function f of x is differentiable. Okay, it's known that f of -4 is 8, f of 2 is 11, f of -6 is 5, f of 4 is -2, and they want you to find this integral. So notice, first off, this is an f prime, and then also notice that if you look at the thing on the inside, if you take the derivative of this, it happens to be this exactly. Okay, so that tells us that we're going to do u sub, and we're going to make this u, because that's perfect, because the derivative is multiplied on the outside. So even if this was a multiple, like, you know, this happened to be exactly the derivative of this inside part, but even if this was a multiple of the derivative of this inside part, that would be just as good. So okay, so this tells us when we're solving this integral, we'll make u the inside. Okay, take derivative both sides. Okay, I have to put that in parentheses because that whole thing gets multiplied by dx. Okay, so just notice that this side, this thing will become u, and then this 2x minus 5 dx together will become du. Okay, so when we do that, this becomes just f of u times du, or f prime of u times du. Okay, and then since this is a definite integral, since it has limits, we'll plug the limits into here. Okay, plug in 4, you get 3. Plug in 2, you get -1. Okay, so now we have to find the antiderivative of our function. So we need a thing that if you take the derivative, we need some function that if you take derivative will give us f prime. So that's just f, right? If you take derivative of f, if you take the derivative of this, you get this. So this is our antiderivative. The thing that if you take the derivative gets you back the original function. So this is an antiderivative. Oh, I kind of messed that up. Sorry. There are these limits I gotta fix. Alright, plug in 4. Oh, the 3 was right. Oh no. Wait, what do I do? Oh, that's x squared. Oh, I don't know what I was thinking. So x squared, so 16 minus 20 is -4. And then 4 minus 10 is -6. Okay, so plug in the top limit, plug in the bottom limit, and subtract. All right, and then they give us those values up top. So that's that one and that one. Wait. Yeah, so this one here and that one there. All right, and then so that's 8, and then -5. Okay, so this next one looks complicated, but let's rewrite it just so we can see it. So, you know, it's hard to say like why I'm going to rewrite it this way. I think you just have to notice that you have an inverse sign, and then you have this square root of 1 minus x squared in the bottom. So that's, you should, you know, whenever you're thinking about inverse sign, think about taking the derivative and you get something like this. You know, you get 1 over this basically. So let's say we just rewrite it just to see it a little clearer. So all I did was just separate the fraction, you know, this numerator from the fraction, really from this denominator. All right, so now we can see super clearly that if we make this u, this exactly is du. So that's what we want. If you make something u, du is everything else that's multiplied, maybe differing by a constant. In this case, this is not even different by a constant. Everything else besides this is, so all of this stuff is exactly du. So now we can just substitute exactly. We don't have to worry about limits. This is just finding antiderivatives. Okay, so this will be integral of u. So just notice that this sine x became u. And really this, actually here, let me do it over here. This sine x became u, and then this got substituted for du. So that's just, this is just u times du. Okay, so now you take antiderivative, and you could think of this as u to the 1. And so you add to the exponent and then divide by that new exponent. All right, and then with that indefinite integral, with definite integrals, you can change the limits so that you don't have to get the integrand back in terms of x. With indefinite integrals, you have to substitute back in terms of x after you take the antiderivative. Oh, I'm sorry, I'm tired. No more integral symbol. Yeah, so right when you find the antiderivative, there's no more integral symbol. That goes away. The du goes away. All right, so now we can substitute u is sine inverse, and we're going to take this and plug that back in for this u. Okay, so now instead of u squared over 2 plus c, this is going to be sine inverse x squared over 2 plus c. Okay, that's whoops. All right, and then since sine inverse, sine negative 1, same as arc sine, it just ends up being this. Okay, so this next one is integral from negative 2 to 2 of x to the 7th plus k dx equals 16, so some little equation, and you want to solve it for k. Okay, so we're basically going to evaluate the left-hand side. It's going to be something in terms of k, and then set it equal to 16, and then solve for k. All right, so we're going to do this like the best way, quickest way, simplest way. So first off, anytime you see a limit that's from a negative number to the same positive number, look out for the trick that I'll hear right off to the side. Trick that if you do an integral from a negative number to the same positive of an odd function, this equals 0. Okay, examples of odd functions. Okay, so x to any odd exponent, so it could be x to the 1, just x. It could be x in negative 1. It could be x cubed, x in negative 3, so on. X to the 5th, x in negative 5th, any odd exponent. Okay, and actually, we'll say also x to the a over b, where a and b are both odd. So even if you have a fractional exponent and the top and bottom, let's say you reduce it, the fraction, and the top and bottom are odd numbers, then that's an odd function also. Wait, I think is that the only other case? Yeah. All right, and then trig functions. So just remember sine and the reciprocal cosecant, and then tan and its reciprocal cotan. Those are odd functions. Okay, so these are pretty much all the odd functions that we deal with. There's tons more, but that's the one that we deal with. So okay, so yeah, so we'll look out. So now we see a negative number to a positive number, and this on its own isn't an odd function, but we could split it up using properties of integrals. Okay, so notice the dx will go with the x to the 7th. And also with the k. So it's almost like first this dx will distribute to each, and then we can split it up, split up the integral. Okay, so nice thing using that trick. We have negative a to a of an odd function. So this just equals 0, this whole thing. All right, so we just have to evaluate this. Okay, so we could do this two ways. Now that we know how to do antiderivatives, you could take the antiderivative of k. K is just some number, like 2 or 10 or something. So the antiderivative k is kx. So you could do that and then plug in the top and bottom and subtract. But I think better is to use the rule when you do a definite integral of a constant. Just do the constant, the constant times b minus a. Okay, so that's like the idea of like when we first learned about finding area. You know, anytime this is a constant, that's just a horizontal line, and when you do limits, when you find area between a constant and the x-axis, that's a rectangle, and so it's really just base times height, and that's what this is, or at least one way to think of it. Right, so this is k times 4. 2 minus a negative 2 is 4, and that means k is 4. Okay, so next one looks weird, but let me see, make sure I can see this. But notice you have, this is kind of this sign is like your outside function, and then you have this other sign that's inside of it. Okay, so let's test to see. Usually we're going to make the thing, if there's something inside of a trig function, usually we're going to make that, other than x, inside of a trig function, usually we'll make that u. And then, so let's test it. So if we make the inside u, so u is sine x, derivative of sine x is cosine x dx, which is multiplied on the outside, so that's perfect. Okay, so we'll make u sine x, so immediately take derivative of both sides. Okay, so just notice that this sine x is u, so that's going to get replaced with u, and then this cosine x dx together is du. Okay, so this will just be sine of u du. All right, now we'll change our limits. So we'll do u of the top limit, u of the bottom limit. All right, so sine of pi over 2 is 1, sine of 0 is 0. All right, and then we'll take the antiderivative. So antiderivative of sine is cosine. But notice if you take the derivative, you get negative sine. So I'll make this a negative to cancel it out. And I'll put that negative on the outside. Okay, and then plug in the top limit, plug in the bottom limit, subtract. Okay, cosine 1. Oh yeah, that's weird. Okay. We can't evaluate, so we'll just leave that as cosine 1. And then cosine 0 is 1. Okay, and then just remember, anytime you do a negative of two things subtracted, all it does is switch the things that are subtracted. So the cosine 1 minus 1 becomes 1 minus cosine 1. Okay. Okay, next one. So if you have a fraction, check to make sure, check to see if maybe the bottom, if you take the derivative, equals the top. So we know the whole bottom, if you take the derivative, since it's got the square root, it's not going to equal 3x squared. But notice, like, even just the inside part of this bottom, so the thing inside the square root. So like if you make u x cubed plus 1, if you take the derivative, you get exactly 3x squared. So that's perfect. Okay, so let's do that. So we'll make u equals Similarly, take derivative both sides. Okay, notice this here is going to get substituted for u, so the bottom will just be square root u. And then this 3x squared dx together becomes du. So the top just becomes du. So that's du over square root u after we substitute. Just notice, right, this whole thing became du, so that's in the top, and then this bottom became u, and that's why it's square root of u in the bottom. Okay, so with indefinite integrals, we'll find the antiderivative in terms of u, and then substitute back for whatever u was to get it back in terms of x's. Okay, first, before we integrate, let's change this to u to the negative 1/2. Okay, now we can integrate. So when any kind of power of u, unless this is -1, but any other number besides -1, just add 1 to this. And okay, so if you add 1 to negative 1/2, you get 1/2. And then you could think of it as dividing by 1/2. You know, always divide by the new exponent that you get. But better if you have a fraction, just multiply by reciprocal right away. So reciprocal of 1/2 is 2 over 1, which is just 2. And so we'll do that. All right, and then u is x cubed plus 1. So now it's back in terms of x's. And then they wrote all the answers as square roots. And so we will. Right, and becomes this one. Okay, so a lot of times when you have fractions, you'll make u the bottom. So let's test it. So if u was x squared, so the derivative of x squared is 2x, and here you have an x, which is good. This is a derivative, this is a 2x, and this is an x, so that's good because it differs by a constant. But if you have something added or subtracted, that's no good anymore. So we can't make this u because du is not the thing that's multiplied. In this case, just in the top, since it has this -4. All right, so we can't do u sub for this one. All right, so we got to think of some other way. So almost always, not almost always, but a lot of times, if you have, if you have things added or subtracted, you can have a bunch of things over a monomial. You can split it up and then just integrate each one separately. All right, so that's what we'll do with this one. Okay, make two different integrals. I'll do the x over x squared, and then -4 over x squared, and then we'll just have dx's with each one. Okay, and then maybe we'll simplify. Okay, so this x over x squared is 1 over x. Okay, and then we can rewrite this as x to the -2. And I'm actually also going to pull this 4 out. You don't have to, but okay, and then now we'll evaluate. Okay, and actually I didn't have to split this up. Maybe I actually shouldn't have split this up. Here, we could do it this way, but we're erase this just to see our options. So let me do this. Okay, I don't know why I did that, but normally you just kind of do it like this. Just keep it all one integral. Okay, it's an integral from 2 to 1. Okay, so now we'll integrate. The integral of 1 over x is ln absolute value of x. All right, and then you'll add 1 to the exponent and divide by the new exponent. So add 1, you get negative 1. X and negative 1. And then technically you divide it by negative 1, but we'll, when we're dividing by negative 1, we basically are just multiplying by negative 1, and that'll make that a plus. So we'll just make that a plus right now. Okay, so now we'll plug in the top limit. Don't need the absolute value since that's just going to be a positive 2 anyways. Hopefully you can see that. Okay, ln of 2, we don't know what that is, so we'll just leave it as ln 2. Okay, 2 to the negative 1 is 1/2. Oops. And then 1/2 times 4 is 2. Okay, and then this ln of 1 is 0, so this is minus 0. And then this is 4 times 1 to the negative 1 is just 1. 4 times 1 is 4. So this still be a minus. That negative will distribute. That. Okay, and that's it. All right, next one. You could do 2 different ways. You could notice like this inside part, if you made this u, so the derivative of x squared plus 2 is 2x dx, and here you have an x dx, which is good. Just so the derivative of the inside is the outside, but just differing by a constant multiple. So you can make u this inside part. You could also FOIL all this out. You'll end up with 3 terms, some polynomial, and then just do 3 separate power rules. So doesn't matter, do it either way. I think just one's just as good as the other. I think U sub might be a little quicker, but it's not that much better, so I don't think. Okay, take derivative both sides. Okay, here we have a 2x dx, but in our integrand we only have an x dx, so we'll get rid of this 2, multiplying 1/2 to both sides. Okay, now we notice this x squared plus 2 is what we're calling u, so that'll get substituted, that'll become a u squared. And then this x dx together becomes 1/2 du. So this will become u squared times 1/2 du. Okay, the 1/2 I'll pull out. All right, and then we'll remember to change our limits if we have a definite integral. So we'll take u of the top limit, u of the bottom limit. So plug in 1, you get 3, 0, you get 2. All right, the integral of u squared, add 1 to the exponent, divide by new exponent. Okay, and then plug in the top limit. the bottom limit. Subtract. All right, 3 cubed is 27 over 3. 27 divided by 3 is 9. And then 2 cubed is 8, so that's 8 over 3. All right, and then, actually I probably should have left it as 27 over 3, since we have a common denominator. Okay, and then 27 minus 8 is 19. So that's 19 over 6. Okay, next one. When you first look at it, it might look maybe like an inverse trig function. But if this was a derivative inverse sine, this would be a minus and this would be squared. If this was the derivative of inverse cosine, it wouldn't have a square root and the x would be squared. So this is not an inverse trig function. So, okay. All right. So with practice, you could do this without u sub, but let's do u sub. So notice if you make u this inside part 1 plus x, derivative 1 plus x is just dx, which is everything else on the outside. Okay, so that tells us that's a good thing to make u. Okay, immediately take derivative. All right, and then just notice this dx becomes du. The dx will get substituted for du. Actually, here, sorry, this 1 plus x will become u, and the dx will become du. Okay, so this will be du over square root of u. Okay, so we'll change our limits. Oops. All right. This will become a 9 and a 1. Okay, so any just like with derivatives, any roots you have to change to fractional exponents, and then if it's in denominator, we'll make it negative. This will become u to the negative 1/2 du. Okay, so now we could take antiderivative. If your function's variable to a constant power, just add 1 and divide by the new exponent. So you'll get u to the 1/2. Right, negative half plus 1 is 1/2. And then fractional exponents, better to just, you could divide by 1/2, but at the same time, same thing as multiplying by reciprocal. And so reciprocal 1/2 is just 2. All right, I'm even going to pull that 2 out. Okay, you don't have to make a whole nother step for that, but just to see what's really going on. Okay. So then plug in 9. So 9 to the 1/2, same as square root of 9. So that's 3. And then plug in 1. 1 to the 1/2 is 1. Square root of 1 is 1. All right, so this last one. So let's say we were thinking maybe this is u sub. So definitely make u the thing inside the parentheses. So if you make u x plus 1, the derivative of x plus 1 is dx, which is here, but then we have this extra term, so this isn't a u sub problem. All right, so this is one, when we did that classwork, this would be rewriting the integrand or simplifying the integrand or something like that. So this will be one where we'll distribute we'll distribute this, and then, yeah. All right, so this is an x to the 1/2 times the x to the 1, which is x to the 3/2, just to add the exponents, and then plus x to the 1/2 times 1, x to the 1/2. All right, so now we'll add 1 to the exponent, divide by the new exponent, which same as times it by reciprocal. Same with the other one, add 1 to the exponent, times by reciprocal. Okay, and then if we plug in 1, these just become 1s, you know, so really it's just 2/5 times 1 plus 2/3 times 1, which is 2/5 plus 2/3. And then if you plug in 0 for each of these, it's just 0, so technically you're just doing -0. So, all right, and then find common denominator. So this would be 6/15 plus 10/15.